Welcome to the next session. In the last session, we have discussed mean, variance, and standard deviation of discrete random variable. So mean value is very clear. E of x value is x1 into p of x1 plus x2 times p of x2 plus and so on plus xn into p of xn. Let me write out what we had in the last session. E of x equal to summation I equal to 1 to n xi dot p of xi. This is expectation of a discrete random variable. Variance is given by this. Sigma x square is E of x square minus E of x whole square. And standard deviation is positive square root of this, that is plus sigma x. So these are the three statistical parameters which describe a random variable very clearly. Basically, mean is nothing but average value. Suppose when you look at average of a particular student in case of marks. Suppose let us take average marks of a 10th class student. Then they will be having some 6 to 7 subjects, say for example 6 subjects. So M1 plus M2 plus M3 plus M4 plus M5 plus M6 marks in subject 1, marks in subject 2 and so on, marks in subject 6 divided by 6. That gives average marks in that academic year. So variance, how much each individual subject marks is deviated from original mean value. What is the standard deviation? So when I go to statistical part, you can easily understand why we were discussing mean, variance and standard deviation. So generally we can discuss mean value, variance and standard deviation for random variables and even for data of some sample points. Okay. Now this is expectation, variance and standard deviation of a discrete random variable. Suppose if I have a continuous random variable. So continuous random variable, assume that the PDF is f of x. So that means f of x is nothing but a probability distribution function. In case of discrete random variable, probabilities will be mentioned individually to all the sample points. In the last session, we have seen probabilities of discrete random variable. Probability of 1, 0.7, probability of point number 2 is 0.3. That means individual probabilities will be mentioned very clearly. But in case of continuous random variable, we have infinitely many sample points. So it may not be possible to describe probabilities of each sample point very clearly. So in that case, all probabilities will be specified by a function in the single variable x, that will be PDF. Therefore, when x is a continuous random variable with a PDF f of x, then what is expectation of x? The expectation of x is, in case of discrete random variable, this is summation. But in case of a continuous random variable, it is integral minus infinity to plus infinity x into f of x dx. So this is the expectation of a continuous random variable with a PDF f of x. That sigma is replaced by integral. Since it is continuous random variable, it is running on entire x-axis. So limits are ranging from minus infinity to plus infinity. This is xi. This is sample point. This is PDF. This is PDF. But in place of sigma, we get integral from minus infinity to plus infinity. And variance is as usual. Sigma x square is E of x square minus E of x whole square. But this E of x square is integral minus infinity to plus infinity x square into f of x dx minus this E of x is integral minus infinity to plus infinity x into f of x dx whole square. Now standard deviation. Standard deviation is positive square root of variance, that is plus sigma x. So note all these points. We discuss mean, variance, standard deviation for CRV. You can write it as a note. Note, if x is a CRV, if x is a CRV with a PDF f of x, if x is a CRV with a PDF f of x, with a PDF f of x, then write these points, point 1, point 2 and point 3, mean, variance and standard deviation. Now look at the variance of random variable. So the same formula we were using for both discrete and continuous random variables. So here we have a minus symbol. Even though if we have minus symbol between these two, the variance of any random variable is always greater than or equal to 0. Most effective point. The variance of any random variable is always non-negative. Note the variance of any random variable is non-negative. The variance of a random variable is non-negative. Now let us make a few comments on discrete random variable at first. Suppose x is a DRV. X is a discrete random variable with a PDF like this: x1, x2 and so on xn. The probabilities are given like this: p of x values, p of x1, p of x2 and so on p of xn. So this is the PDF of a discrete random variable x. PDF of a discrete random variable x. Now point 1, add all these probabilities, the result is 1. That is p of x1 plus p of x2 plus and so on plus p of xn. This result will be always 1. So it is summation, that is sigma I equal to 1 to n p of xi, general sample point I. So therefore it is 1. Sum of all probabilities of a discrete random variable is always 1. Next, suppose I want probability that x is less than or equal to xi. Probability that the random variable x is less than or equal to xi. Less than or equal to means at most. So at most. What is the starting sample point? X1. So maximum sample point will be xi. So therefore this is nothing but sum of p of x1, p of x2 and so on p of xi. P of xi. So maximum sample point is xi only. See, suppose I have sample points like this: x12 and so on x20. Suppose if I ask you what is p of x less than or equal to x, for example 16. So I have sample points x1 to x20. If I ask you what is p of x less than or equal to x16, you consider all sample points from x1 to x16 only. P of x1 plus p of x2 plus and so on plus p of x16. So therefore p of x less than or equal to xi is p of x1 plus p of x2 plus and so on p of xi. This is nothing but 1 minus of p of, what is the sample point after xi? Xi plus 1. So 1 minus of p of xi plus 1, p of xi plus 2 plus and so on plus p of xn. This result we get only from this, because sum of all probabilities is 1. Therefore p of x1 plus p of x2 and so on plus p of xi is 1 minus of probabilities of remaining sample points. Now next one is p of x greater than or equal to xi. So greater than or equal to means at least. So starting sample point will be xi. So therefore this is p of xi plus p of xi plus 1 plus and so on. This is xn. And the fourth point we have is p of xi less than or equal to x less than or equal to xj. Don't think that the index j is immediate to I. This I can be 7, j can be 9, I can be 4, j can be 10, like this. So you consider all sample points from xi to xj. So therefore this gives p of xi plus p of xi plus 1 plus and so on plus p of xj. So these are very, very important points. So you write all these points. This is the PDF of a discrete random variable. Then you will get 4 conclusions: 1, 2, 3, 4. Note all these points. The same points for continuous random variable. Suppose x is a CRV. X is a CRV with a PDF f of x. then instead of summation we get integral value. Therefore this equation, point number 1 becomes integral minus infinity to plus infinity f of x dx must be 1. So integrate a PDF on entire x-axis, the result will be 1. Now the second expression, this is p of x less than or equal to a. Probability that the random variable x is at most a. So here upper limit is a, but lower limit of continuous random variable is minus infinity. So this will be integral minus infinity to plus a f of x dx. Now third point is p of x greater than or equal to a. So here lower limit is a, but upper limit is infinity. So therefore this is integral a to infinity f of x dx. Now when you look at this, p of a less than or equal to x less than or equal to b. That means random variable lies between the sample points a and b. In that case, this becomes integral a to b f of x dx. Integral a to b f of x dx. Now you can see in case of continuous random variables, all probabilities are expressed in terms of definite integrals. But basically, what do you mean by integral? Integral a to b f of x dx represents area bounded by f of x between two boundaries of straight lines. So in general, the probabilities of continuous random variables are nothing but areas of certain curves, right? So note all these points. Note, if x is a CRV with a PDF f of x, if x is a CRV with a PDF f of x, then write all the points 1 to 4. One more point on continuous random variable. Suppose x is a CRV with a PDF f of x. So this is the PDF of a continuous random variable x, and g of x is any function in terms of x. Then expectation of g of x is given by integral minus infinity to plus infinity g of x into f of x dx. Suppose if I write expectation of continuous random variable x, then e of x becomes simply integral minus infinity to plus infinity x into f of x dx, where f of x is a PDF of CRV, but if it is x, I will get x. If it is a general function g of x, then this x is replaced by g of x. Therefore the conclusion is, if x is a CRV with a PDF f of x and g of x is any function, then expectation of g of x is this. Note this point. Now if x is a CRV with a PDF f of x, if x is a CRV with a PDF f of x, with a PDF f of x, and g of x is any function, and g of x is any function, then e of g of x equal to, then e of g of x equal to integral minus infinity to plus infinity g of x into f of x dx. E of g of x equal to integral minus infinity to plus infinity g of x into f of x dx. Now with this we have finished all basics in discrete as well as continuous random variables. Next we move to new concept, that is functions. Now let me tell you how functions and sets are very useful to our probability. Basically, you may get some doubt how functions are related to probability, how sets are related to probability, right? Let me ask you one simple question. Suppose a student is ready to appear an examination, semester examination involving 6 subjects. So for example, subject 1, subject 2, subject 3, 4, 5, 6. A student is ready to appear semester examination involving 6 different subjects. Now, what is the probability that a student will fail in at most 2 different subjects? What is the probability that a student fails in at most 2 different subjects? Probability that student fails, or probability that student will fail in at most 2 different subjects. In at most 2 different subjects. Now, how to handle this question? So there is one student who is ready to appear semester examination involving 6 different subjects, 1, 2, 3, 4, 5, 6. So what is the probability that that particular student will fail in at most 2 different subjects? So the answer will be like this. Here the sample space S will be like this. So total number of subjects he or she ready to write is 6 subjects, right? But in how many subjects he is getting to be failed? At most 2. At most 2. That means the student may fail in only 0 subjects. That means empty set. Or he may fail in 1 subject. That means he may fail in only subject 1, or only subject 2, or only subject 3, or only 4, only 5, only 6. Only single failures in each subject. Or he may fail in 2 subjects. For example, 1, 2. Subject 1, 3. These are various chances. 1, 4, like this. So basically this is nothing but subset of S having 0 elements. All these are nothing but subsets of S having single element. All these are subsets of S having 2 elements. Therefore, what is the probability that student will fail in at most 2 different subjects? So this is 60 naught. That means student is not failing in any one of the subjects, or student may fail only in 1 subject. So 61. Or means plus student may fail in 2 different subjects divided by total number of chances. So basically all these are subsets of S. When you take a set of 6 elements, the total number of subsets of S is 2 power 6. Therefore this is 1 plus 6 plus 62 is 6 into 5, 30 by 2, 15, divided by this is 64. Therefore this is 22 divided by 64. So therefore the probability is 11 out of 32. Therefore the probability that the student will fail in at most 2 different subjects is 11 by 32. You see how the concept of sets are very useful in case of solving probability questions. So sets are very powerful. So don't neglect sets. Sets are very powerful. Even functions are very useful for us. Functions are very useful. Sets, functions, everything is very useful for probability class. Okay. So I think did you understand this? So a student is ready to appear a semester examination involving 6 subjects. Say 1, 2, 3, 4, 5, 6. Now my question is, what is the probability that student will fail in at most 2 subjects? So at most 2. That means student may not fail even in single subject, or he or she may fail only in 1 subject, or student may fail at most 2 subjects. So therefore chances are like this. Basically all these are subsets of S. This is a subset of S. Basically it means that the student is failing in subject 1 and subject 2. Student is failing in subject 1 and 3. So basically all these are subsets of S having 2 elements. Subsets of S having single element. Subsets of S having 0 element. That means student may fail in 0 subjects, or student may fail in only in 1 subject, or student may fail in 2 different subjects. So therefore the required probability is 60 naught plus 61 plus 62 divided by total number of subsets of S, that is 2 power 6. The probability becomes 11 by 32. So this is the beauty of probability in terms of sets. So even you can apply functions. Functions is nothing but combinations of sets. Okay. During solving gate questions, you can easily understand the importance of functions as well as sets. This is one beautiful example of comparing sets and probability. Let us see what is the concept of a function. Suppose we have 2 sets A comma B, and we have a mapping F from A to B. So F is a mapping from A to B. F is a mapping from A to B. That means map every element of A to elements of B. So just that is mapping is your own choice. Let us say, for example, the set A is like this. Set A contains 3 elements. Set B contains, for example, 4 elements: alpha, beta, gamma, delta. So 1 is mapped to beta, 2 is mapped to gamma. Now you can see elements of A are mapped to elements of B. So it is a mapping. So we call it as this mapping as F. It is a mapping but not a function, because 3 is not at all mapped to any element of B. So it is a mapping but not a function. This is a mapping but not a function. Now I go for another mapping between same sets. So set A is 1, 2, 3. Set B is alpha, beta, gamma, delta. 1 is set to alpha, 2 is set to alpha, 3 is set to delta. Now you can see this is a mapping and it is again a function, because every element of A is associated with exactly one element of B. Every element of A is mapped with exactly one element of B. Therefore, this mapping is called a function. Now in this case, suppose if this is F, here we can write like this: f of 1 equal to alpha, f of 2 equal to alpha, and f of 3 equal to delta. That means when you consider this f of x equal to y, that means image of x under f, image of x under f is y, and pre-image of y under f equal to x. Therefore, what is the image of 1? Alpha. Image of 2? Alpha. But what are the pre-images of alpha? They are 1 and 2. So every element will have exactly one image, but the element in the second set can be acting as image for multiple elements. Therefore, in this case, if we have two sets A and B, we have two sets A and B. They can be finite or infinite, but generally probabilities can be measured only for finite sets. So assume that there are some finite sets. But if function is defined for two infinite sets also. So we have two sets A and B, and there is a mapping F from A to B. We say that a mapping F from A to B is a function if every element of A is mapped with exactly one element of B. Now this is a mapping but not a function, because 3 is not at all mapped to any element of B. Suppose if I give this example 1, 2, 3, for example alpha, beta, gamma, delta between same sets A, B. So 1 is mapped to alpha, 1 is mapped to gamma, 2 is set to beta, 3 is set to delta. Now one particular element, 1 is having multiple images. 1 is set to alpha, 1 is set to gamma. So it is again a mapping but not a function. This is again a mapping but not a function. Mapping but not a function. But this is a mapping, also a function. Also a function. So whenever we have a function F from A to B, whenever we have a function from A to B, then the first set A is called domain. Domain. That means for what values of A, function is valid, and B is called codomain. B is called codomain. And whenever f of x equal to y, if f of x equal to y implies image of x under f is y, pre-image of y under f is x. So write these points. Let A comma B, put the heading function. Let A comma B be two sets. Let A comma B be two sets. And f be a mapping from A to B, and small f be a mapping from A to B. Small f be a mapping from A to B. We say that let A comma B be two sets, and small f be a mapping from A to B. Small f be a mapping from A to B. We say that f is a function from A to B. We say that f is a function from A to B if every element of A, we say that F is a function from A to B if every element of A is mapped with exactly one element of B. We say that F is a function from A to B if every element of A is mapped with exactly one element of B. If every element of A is mapped with exactly one element of B. So you write the examples. First example, it's a mapping but not a function. Because why it is so? Because one has more than one image. One has more than one image. Here it is a mapping but not function because 3 has no image. So example 1 followed by reasons, example 2 followed by reasons, and example 3, this is a mapping and even a function also. Actually, in simple words, I can say that y is not a function. You can see how 1 is distributed to both alpha and gamma. A single item, actually these are distributions from one set to another set. So these 1, 2, 3 can be chocolates. Alpha, beta, gamma, delta can be human beings. Okay. Or these 1, 2, 3 can be books. They can be human beings like this. So how a single quantity can be distributed to alpha and gamma at a time, it is not possible. So in this case 3 is not at all distributed. So therefore these two are not functions, but that can be possible. Here book 1 can be distributed to person alpha. Even second book can be given to person alpha also. Third book is distributed to only delta. So no other book is distributed to beta and gamma. But my intention is whether all books have been distributed to the persons or not. Whether distributions have taken place equally or not, that's immaterial for me. The only important issue for me is whether all books have been distributed to all people. Not all people, whether all books are distributed to certain people or not. But distribution of books must be important. So right now, therefore, in this case, this is a mapping but not a function. Mapping but not a function. It is a mapping as well as a function. Note: if f from A to B is a function, if f from A to B is a function, then A is called domain and B is called codomain. If f from A to B is a function, then A is called a domain and B is called a codomain of f. If f from A to B is a function, then A is called domain and B is called codomain of f. Next note: if f of x equal to y implies, if f of x equal to y implies image of x is y, image of x equal to y, and pre-image of y, pre-image of y is x, and pre-image of y equal to x. Now we discussed one point. Suppose A comma B are two finite sets having m comma n elements. A is a finite set, that means it is having limited number of elements. Assume that it is m. B is having n number of elements. How many possible functions I can define from set A to set B? So as an example of previous, the first set is having 1, 2, 3. The second set is having 4 elements: alpha, beta, gamma, delta. This is one possible mapping. Even this is also a function. This is another function: 1, 2, 3, alpha, beta, gamma, delta. 1 to alpha, 2 to alpha, 3 to delta. This is another function. Like this, how many I can define? So here I have 3 elements, here I have 4 elements. Let us say how many possible functions I can define. So 1 can be distributed to alpha or beta or gamma or delta. So how many possible images are there for 1? So 1 can be set to alpha or beta or gamma or delta. Therefore, one particular this element will have 3 images. So 1 can be distributed to any one of these 4 elements. So 1 will have 4 choices. Similarly, 2 can be distributed to alpha, or 2 can be distributed to beta, or 2 can be distributed to gamma or delta. Again, 2 will have 4 choices. Again, 3 will have 4 choices. Therefore, the total number of possible functions is 4 cube. So the first set is having 3 elements. Second set is having 4 elements. In that case, the total number of possible functions is 4 cube. Therefore, when you generalize this, the first set is having m elements and the second set is having n elements. Then the total number of possible functions from A to B is exactly n power m. Very, very important point. Note this. Note, if A comma B are 2 sets, if capital A comma B are 2 sets having m comma n elements respectively, if A comma B are 2 sets having m comma n elements respectively, then the total number of possible functions from A to B is n power m. Then the total number of possible functions from A to B is n power m. So if I have 3 to 4, 2 choices, but totally we will get 4 cube 81. So 1 will have 4 choices, 2 will have 4 choices, 2 will have 4 choices, and 3 will have 4 choices. 4 into 4 into 4, 4 cube. You write this point. Write these examples, you will get clarification. Why it is n power m. Next one is types of functions. So we discuss first 1 function. It is also called as injection. 1 function. Now out of functions we have various clarifications. Let us see. Suppose we have a function f from A to B. We say that this is 1 if different elements in A have different images in B. If different elements in A have different images in B, then we say that this function is called a 1 function. Let us see. Suppose this is 1, 2, 3. Suppose alpha, beta, gamma, delta. This is A, this is B. Now to define a 1 function, in the first set we have 3 elements. To set 3 different images to these 3 elements, I must have minimum 3 elements in the second set. Because I want to form 1 function, 3 elements are here. So therefore these 3 elements can be distributed to 3 different elements in the second set. Suppose 1 is set to alpha, 2 is set to gamma, 3 is set to beta. So this is a 1 function. Therefore a function f from A to B is said to be 1 if different elements in A have different images in B. At this point, 1 function. It is also called as injection. A function f from A to B is said to be 1 A function f from A to B is said to be 1 if different elements in A have different images in B. A function f from A to B is said to be 1 if different elements in A have different images in B. This is example. This is mapping. Write this example. Suppose A is having 3 elements and B is having 5 elements. In the first set we have 3 elements, in the second set we have 5 elements. How many total functions I can define? Total number of functions is 5 cube, this is 125. So out of these 125, how many functions are 1? This is my question. A and B are 2 sets having 3 and 5 elements respectively. So how many functions are possible at first? 5 power cube. So you will get 125 functions. Out of these 125, how many functions are 1 functions? Let us see. Suppose the set A is like this. This is 1, 2, 3. The second set beta equal to like this. B. Alpha, beta, gamma, for example delta, and for example P, element P. Now I want to define one function between these two sets. Now 1 can be given to alpha, 2 can be given to beta, 3 can be given to gamma. So I will write this representation like this. 1, 2, 3. Image of 1 is alpha, image of 2 is beta, image of 3 is gamma. So this diagram is equivalent to this. 3 different elements will have 3 different images. Therefore, this is a function, of course, one function. Like this, how many? If I extend like this, so 1, 2, 3, alpha, beta, gamma. Then rearrange the terms, images alpha, gamma, beta, beta, alpha, gamma, beta, gamma, alpha, gamma, alpha, beta, gamma, beta, alpha, like this. Now when you look at this, alphas are fixed at first, beta, gamma, gamma, beta. Images are different. So this is one possible image, this is another possible image. So therefore, you select 3. You select any 3 from this and arrange like this. Therefore, to set 3 different images to these 3 elements, you select 3. So selections means combinations. But once you select, you can give the images like this, because this is different from this function. So this is equivalent to this. But when you look at this 1, 2, 3, alpha, gamma, beta. Now this function will be equivalent to like this. A is 1, 2, 3. This is A, and this is B. Alpha, beta, gamma. This is delta. For example, P. 1 is set to alpha, but 2 is set to gamma. 3 is set to beta. Now you can see this function and that function both are different. So this is equivalent to alpha, beta, gamma. I am not changing the positions 1, 2, 3, but alpha, beta, gamma. But 1, 2, 3, this is alpha, gamma, beta. This is another one function. Like this, I can go for permutations. Therefore, you select 3 from 5 elements and arrange like this. Therefore, the total number of one functions is 5p3. Therefore, if I have a set A having m elements and set B having n elements, then the total number of one functions from A to B is npm. This is given by n factorial by n minus m whole factorial. Note these points. If A comma B are two finite sets, if A comma B are two finite sets having m comma n elements respectively, then the total number of one functions from A to B. If A comma B are two finite sets having m comma n elements respectively, then the total number of one functions from A to B is npm. This is equal to n factorial by n minus m factorial. So you can have these examples.